This video is for an assignment for the Automatic Controlling Instrumentation class at Taylor's University. We are going to detail adaptive cruise control, or ACC system, and explore the integration of automation within cars. We are group number 14. My name is Marine-Julie Celia Ouvrard, and my group members are Filippo Sari, Nassim Lenkadem, and Raimi Segui Davalilo. In this video, we will explain what an ACC is and what it's made of. We will explain the operation of each of its components, and to explain more precisely the ACC function, we will show you a flowchart. Then, we will describe its operation from an automatic point of view using a block diagram. We will talk about the potential improvements and limits. We will also try to find ideas to solve them. Let's start with the principle, which is an ACC. As I said earlier, the ACC is the initial of adaptive cruise control. It's a driver assistance system created in 1992 by Mitsubishi Motors. It has evolved greatly since then. It automatically adjusts the speed of a vehicle to maintain a safe distance from the one in front of it. It improves many things like driver comfort, as it minimizes driving fatigue by reducing acceleration during a trip. Second, it increases road safety by preventing collision by maintaining a safe distance and reducing error of inattentions. By reducing unnecessary acceleration, it reduces fuel consumption and helps reduce traffic problems by adopting softer acceleration and slowdown. It is also compatible with other assistance systems such as lane keeping and collision avoidance. As you may have understood, we need a number of components to make the system work properly. First, sensor. The radar sensor detects any obstacle in front of the car and determines the distance between the cars in front and the vehicle. It is usually associated with a camera system. It must have certain specifications such as its tolerance to rain, snow, and extreme heat. Its refresh rate must be very fast to be close to real time, and its range must be at least 200 meters with a wide angle of view. We also need a speed sensor to ensure the speed of our vehicle. Then we need a controller that can manage sensor input, control algorithm, fast calculation and decision making, know when to accelerate and slow down. For this, it must be able to send commands to the different actuators. There are two types of actuators. The first one is the accelerator, also named throttle, reactive to small adjustment for smooth acceleration, operates at a wide range of speed from low speed stop-starts to high-speed trips. The second is the brake, a fast and precise braking to respond to sudden stop or slowdown, soft braking for passenger comfort. Finally, we also need human-machine interface that allows the driver to activate or deactivate the system and adjust parameters such as speed or distance. Now that we have put the context, I will explain the operation of an ACC using a flowchart. As you can see, it starts with the system initialization. Immediately, the vehicle detector will be set up. Once a vehicle is detected, at the front of the car, it will calculate the distance between this vehicle and me. If this vehicle is less than the distance of safety chosen in the parameters, it uses the brake actuator to slow down as long as the distance is not respected. When the safety distance is reached, it will calculate the speed of the vehicle and its own. If these two speeds are identical, then we remain constant. If our speed is higher, we will slow down, and if it's lower, we will accelerate to the speed desired by the driver. As long as the driver does not take control, we will repeat the same step.
Hi, my name is Nassim, and let's take a look to the block diagram of our ACC, our Automatic Cruise Control System. So first of all, the purpose of a block diagram is to represent an integrated control system for a vehicle, in our case, ensuring optimal performances by combining sensory input, data analysis, processing, and actuation. The system begins by gathering data from multiple sources, processes it through a central unit, and produces output that control the vehicle's components such as wheels and braking. So first, let's take a look to our data analysis unit. The first part of the system focuses on collecting data from several sources. The adaptive cruise control, the ACC, provides intelligent speed and distance management. Then the camera system, or the GPS, supplies real-time visual and positional data, and the LiDAR and infrared sensors detect obstacles and surroundings for enhanced safety. These inputs are converted into a usable format, the converter, which prepares the data for further processing. Now let's take a look as well to the processing unit. The data processing unit analyzes the converted data to make decisions. The vector control ensures proper distribution of torque and motion control. The current sensor monitors electrical current to assess motor efficiency and respond to disturbances. The system interacts with speed sensors and evaluates external disturbances to adjust vehicle operation dynamically. That's why there is a loop, as you can see. Now let's take a look to the output and operating units. The final stage involves the operating unit, which translates processed data into actionable outcomes. The PID brake and PID throttle. It goes through one of them. It's used to precisely control braking and acceleration to maintain stability and safety. Then there is a transformer and the wheels to implement the control commands by adjusting wheel dynamics for smooth and efficient vehicle movement. Additionally, vehicle-to-vehicle (V2V) communication enables coordination with nearby vehicles to enhance overall traffic management and safety. This breakdown highlights how the system combines sensor input, intelligent processing, and actuation to ensure efficient and safe vehicle operation. That's all for the ACC. Hi, my name is Nassim.
I'm Filippo, and right now let's discuss some critical challenges faced by adaptive cruise control systems. The first challenge is fault detection due to environmental factors, so ACC systems can rely heavily on radar sensors to detect vehicles ahead. However, this sensor can struggle in the adverse weather conditions such as rain, fog, snow, and even bright sunlight. Radar signals can scatter, reflect, or be blocked by debris like dirt or ice on the sensors. Or, for example, during heavy rain, the system might misinterpret the environment, causing unnecessary braking or failing to detect vehicles accurately. And these fault detections can disrupt driving comfort and potentially cause dangerous situations. As the second problem, we got a slow response in heavy traffic. So ACC systems may respond slowly in congested traffic conditions. If a vehicle suddenly cuts into the lane, the system might take a few moments to process the change and adjust the car's speed. This delay can cause sudden braking, increasing the risk of collisions. The third problem is limited detection range. So, for example, at high speeds, the vehicle needs to detect obstacles far ahead to have enough time to respond. And if the range is limited, so the system might react too late, leading to dangerous situations, especially on highways where the vehicles travel at high speeds. As the fourth problem, we got sensor calibration errors. So calibration errors in sensors can significantly affect ACC performance. If sensors are not properly aligned due to manufacturing defects, repairs, or even regular wear and tear, they may provide inaccurate readings. For the fifth problem, we got complex road scenarios. So ACC systems can face challenges when navigating complex road scenarios, including intersections, sharp curves, and merging lanes. These situations involve unpredictable vehicle movements, which can confuse the system and lead to delayed or incorrect responses. And as the last one, we got the driver over-reliance. The convenience of ACC can lead the driver, in fact, to over-reliance. When drivers trust the system too much, they may become less attentive, expecting the car to handle all the driving tasks. And this over-reliance is dangerous as the system still requires human intervention in emergencies. So our proposed solutions are the following ones. For the first problem, we got sensor fusion technology. So combining data from multiple sensors such as radar, cameras, and LiDAR can improve the system's understanding of its environment. So for example, while radar might struggle in foggy conditions, cameras can still identify lane markings and detect nearby vehicles. And this integration can reduce false positives and improve accuracy. For the second problem, we got predictive control algorithms. So advanced algorithms can analyze real-time data and predict vehicle behavior based on historical patterns. These allow the system to anticipate sudden stops or lane changes, enabling smoother adjustments and reducing abrupt braking. For the third problem, we got enhanced detection range. So upgrading radar sensors with extended range capabilities can help detect vehicles farther ahead. These allow the system to react earlier, improving safety at high speeds. For the fourth problem, we got automated sensor calibration. So automatic calibration routines can be integrated into the vehicle's software to ensure sensors remain accurate over time, and drivers can also receive alerts when manual calibration is needed. For the fifth problem, we got advanced road mapping. So incorporating high-definition maps and GPS data allows ACC systems to anticipate road features such as intersections, sharp curves, and merging lanes. This information can help the system adjust proactively, ensuring a smoother driving experience. And for the sixth problem, and so the last one, we got the solution of driver monitoring systems. So installing driver monitoring systems can detect signs of fatigue, and if the system senses that the driver is not paying attention, it can issue alerts or take corrective actions to encourage driver engagement. So by implementing this solution, ACC systems can become more reliable, safer, and better equipped to handle real-world driving scenarios. For the
After having all these challenges and solutions explained to you by my classmate, we decided to implement two main things to our block diagram to create or improve the ACC block diagram. We implemented LiDAR and infrared sensors. LiDAR sensors offer a higher resolution detection, which ensure reliable performance in challenging weather, while the infrared sensors improve visibility in low light or night driving. We also implemented a vehicle-to-vehicle communication, also known as a V2V. This will get the live information from the vehicle in front, such as braking, accelerating, etc., and it will feed back the information back into the automatic cruise control system for better understanding of what the vehicle in front is doing. So if per se, the vehicle in front suddenly brakes, the information of the speed of the car ahead will immediately be recorded by the car, and the adaptive cruise control system will take the appropriate measures, in this case, reducing the speed. The benefits of our improved ACC system are basically three main benefits. First of all, enhanced detection accuracy in adverse conditions. As we explained, the LiDAR integration it offers high resolution detection, ensuring reliable performance in challenging weather, such as fog, rain, or snow, while the infrared sensors improve visibility in low light or night driving, enhancing system robustness. Increased responsiveness to sudden changes is another benefit, which with vehicle-to-vehicle communication, the V2V, we get real-time feedback from the vehicle ahead, such as speed, braking, acceleration. But this also minimizes reaction delays to sudden braking or rapid acceleration. The third benefit is improved safety, especially at high speeds. This extended detection range with LiDAR allows earlier obstacle detection, especially on highways. It also reduces risks of delayed braking or collision at high speeds. The adaptive cruise control system integrates three main things: sensors such as radar and speed sensor, a controller, and actuators such as the throttle actuator and brake actuator. The challenges faced by the adaptive cruise control system are a false detection due to environmental factors such as fog and rain, and a slow response. Solutions to these challenges are the addition of a LiDAR, infrared sensors, and V2V technology for real-time vehicle-to-vehicle communication. The benefits of the improved system are enhanced detection accuracy and responsiveness. Thank you very much for your attention, and this is all.